Welcome to Lesson 3 in your virtual test prep, Flight Instruments. Now, flight instruments convey critical flight data, such as the airplane's position, altitude, speed, and other important parameters during every phase of flight. This lesson explains how these instruments function and details their limitations. Understanding these concepts is vital to properly interpret instrument indications. These instruments fall into 4 general categories based on system technology and sensor type. These are the pitot-static, gyroscopic or vacuum, electronic, and magnetic compass systems. Now, ever since early aviation, pilots relied on instruments employing mechanical and/or electrical gauges with dials and pointers. Now, computer-processed flight data is presented on computer screens, also known as glass cockpit displays. These glass cockpits are installed on virtually all newly manufactured aircraft. Although the display technology may differ between these systems, the sensors and data presented is very similar, or in some cases even identical. The FAA expects pilots to understand these concepts regardless of the technology employed and focuses more on the traditional display gauge implementation in the knowledge tests. Now, in this lesson, we'll cover the pitot-static system, airspeed indicator, airspeed limitations, vertical speed indicator, altimeter, types of altitudes, gyroscopic instruments, magnetic compass, compass errors. All right, let's join your instructor now for the pitot-static system.
The pitot-static system consists of 2 major components. One is the impact pressure chamber and its associated lines that originate with the pitot tube, and the other is the static pressure chamber and its corresponding lines that originate with the static port. Now, both of these components are found on the aircraft's exterior. They're the source of ambient air pressure for the operation of the altimeter and the vertical speed indicator, as well as the impact pressure for the airspeed indicator. Check this example. The pitot tube receives ram air pressure or impact pressure, which is the result of the airplane's pitot tube being struck by air as it moves forward. This ram air pressure moves up into the airspeed indicator. Now, static air pressure information is also provided by the static port. It provides the reference source for ambient air pressure. Ambient air pressure is the static air pressure outside the aircraft. Now, ram air pressure is sensed by the pitot tube and displayed by the airspeed indicator. The ambient air pressure is sensed by the static port. It's the difference in these 2 pressures that is displayed as indicated airspeed on the airspeed indicator. In the event that the pitot tube is blocked, say by a bug, dirt, or some kind of debris, the airspeed indication will not be accurate. Instead, the airspeed indicator functions like a barometer. In other words, the higher we fly, the less the air pressure. Therefore, you'll see an erroneous reduced airspeed. Conversely, if you're flying at a low altitude and the pitot system is blocked, there will be higher air pressure. This condition will manifest itself as an incorrect higher airspeed indication. Make sure the pitot tube and the static port are both clear of debris during your pre-flight inspection. The next instrument in the pitot-static system is the vertical speed indicator, or the VSI. Now, the VSI measures the rate of climb and descent in hundreds of feet per minute, and it operates from the static port alone. As the airplane climbs and descends, the vertical speed indicator measures that rate of change with air pressure. The third instrument is the altimeter. The altimeter measures the height above sea level. It also operates from air pressure in the static port system. It's simply a barometer. The higher you fly, the less air pressure there is. Less air pressure will be indicated by a higher altitude.
Okay, let's take some time to cover a question on the pitot-static system. The question is, which instrument will become inoperative if the pitot tube becomes clogged? 3 potential answers, only one of which is correct. Take a look at each. Again, which instrument will become inoperative if the pitot tube becomes clogged? The answer is C, airspeed. Remember, the pitot tube provides input for the airspeed indicator only. If the pitot tube becomes blocked, It's going to give you an inoperative airspeed indication. With that, let's rejoin Josh in the classroom for the next topic, airspeed indicator.
Now let's take a detailed look at our three instruments on the pitot-static system, and we'll start with the airspeed indicator. First, notice a series of color-coded arcs on the airspeed indicator's face. The white arc, green, yellow, and then this red line right over here. These are operating limitation ranges or operating limits of your airplane. Depending on what airplane you fly, these arcs and airspeeds will differ, but you will see these color-coded arcs on each and every airplane. Now, the airspeed you read directly from the airspeed indicator is called the indicated airspeed. Airspeed that is corrected for installation and instrument error is called calibrated airspeed. The true airspeed of an airplane is calibrated airspeed corrected for variations in temperature and pressure. Now, the true airspeed is used for flight planning purposes and will be discussed in greater detail in Lesson 9. Now let's take a look at some airspeed limitations, and we'll start with the white arc that you see right here. The white arc represents the flap operating range in your aircraft. At the bottom of the white arc is the airspeed limitation called VSO. Now, the V stands for velocity or speed, and in this case the S stands for stalling. Now, the O stands for operation in a certain configuration, and in this case that configuration is the lowest allowable airspeed with the flaps and the landing gear down, or the landing configuration. Operation below this airspeed in the landing configuration will allow the airplane to stall. Now, at the top of the white arc is the airspeed limitation called VFE. You can see that right here. Again, we know the V is for velocity, the F is for flaps, and E is for extension. Now, this is the maximum speed at which flight is allowed with the flaps extended. Let's take a look at another one. Here is VS1. And in this case, we know that V is for velocity again, S is for stall, but this is configuration 1. This means that with the flaps up, or in a clean configuration, if you fly below this airspeed with flaps up, the airplane will stall. Remember this, VS1 is the stalling speed in a clean configuration, and VSO is the stalling speed in the landing configuration with the flaps and gear down. Now, the green arc represents the normal operating range of the aircraft. At the top of the green arc is a speed called VNO. You can see that right here. That is really the highest allowable airspeed under most operating parameters. You may from time to time head into the yellow arc if the air is very smooth, but just like a street sign, remember that yellow means caution. Now, if the air gets bumpy, reduce your speed to a speed within the green arc. Now, the yellow arc represents something called the caution range. Operating at airspeeds in this range requires caution, and you should only fly at these speeds in smooth air. At the very top of the yellow arc is a red line. We call this red line VNE. Now, the V again stands for velocity, N is for never, and E is for exceed, which means never exceed speeds above this red line. If you do, you risk the likelihood of structural damage to the airplane. Now, there are also some airspeed limitations that are not marked on the airspeed indicator, but you need to know them just the same. First of all, VA is for maneuvering speed, and this is the speed at which full control deflections will not cause structural damage to the airplane. The airplane will stall before G-loads can cause damage. VA, or maneuvering speed, can be found by looking in the pilot's operating handbook for the particular airplane you're flying. Another airspeed limitation not depicted on the airspeed indicator is VLE, which is the maximum landing gear extension speed. This is the maximum speed you can safely lower the landing gear on an aircraft with retractable gear. Again, this speed is found in the pilot's operating handbook. Another speed is VX, and that's the best angle of climb speed. It provides the greatest altitude gain for a given distance. Finally, VY is the best rate of climb speed. It provides the greatest altitude gain for a given period of time. In this example, our airplane is rolling for departure. If you have an obstruction at the end of the runway, you need to make sure you can climb at VX, which is the best angle of climb speed. This airspeed allows the airplane to gain the greatest amount of altitude in a given distance. Once we've cleared the obstruction, we can transition to a speed of VY, which is the best rate of climb speed. This airspeed provides the most altitude gain over the least amount of time.
Okay, let's take a question on the airspeed indicator and its limitations. What is an important airspeed limitation that is not color-coded on airspeed indicators? Please take a look at the three potential answers. Only one is correct. All right. Once again, what is an important airspeed limitation that is not color-coded on airspeed indicators? The answer is C, maneuvering speed. The never exceed speed is identified by the red line, and the maximum structural cruising speed is found by the upper limit of the green arc. All right, let's get back in the classroom with Josh and a new topic, vertical speed indicator.
Next, we'll talk about the vertical speed indicator, or the VSI. Now, the VSI measures the rate of climb or descent in hundreds of feet per minute. For example, 500 feet per minute, 1,000 feet per minute, and so on and so forth. The VSI, or rate of climb indicator, is a very sensitive altimeter incorporating a device called a calibrated leak. As you climb and descend, this instrument measures outside ambient air pressure from the static port. At the conclusion of a maneuver, the VSI does have a tendency to lag a little bit, so do be aware of that. Next, let's take a look at the altimeter. You can see an example shown right here. The altimeter indicates your height above mean sea level, also called MSL. Now, there are three pointers on the altimeter. You can see those shown right here, and there's a little cutout window right here. That's called the Colesman window. The Colesman window is used to set the current barometric pressure. The current barometric pressure, often referred to as the altimeter setting, is provided by the tower or directly to the pilot by an ATIS or ASOS broadcast. This data is set directly into the Colesman window. Now, if you are departing from an airport that does not have these services, simply set the dial to the field elevation from which you are departing. This way, you'll get a fairly accurate indication of your altitude above mean sea level, or MSL. Now, let's take a closer look at the altimeter pointers. Just like a wristwatch, we have three hands, but instead of indicating hours, minutes, and seconds, in this case we have a 10,000 foot, a 1,000 foot, and a 100 foot hand. This 10,000 foot hand, on this particular example, is not quite yet to the 1, so we know that we have less than 10,000 feet shown on this altimeter. Now, if we look at our 1,000 foot indication, we can see here that it's just past the 2, so we know we're at least more than 2,000 feet. And finally, if we look at our third hand, that's our 100 foot hand. That shows that we're just about on the 5. So we are at 2,500 feet mean sea level, or MSL.
Okay, let's cover a question now on the altimeter. Now, on this particular question, the FAA is going to provide you with a graphical representation of the altimeter too. But the question is, the altimeter 2 indicates which of these three potential answers? Again, only one is correct. Now, let's take a look at that graphic. Here it is. Each of the hands, there are three, represents a different altitude. So we're at tens of thousands of feet with the shorter hand. The fatter hand pointing at the 4 is in the thousands of feet, and the longer hand pointing at the 5 is hundreds of feet. So we've got 14,500 feet reading on this altimeter, correct? Okay, back to our question. Altimeter 2 indicates which of these three? Correct answer, C, 14,500 feet. And it's that simple. Just read the three hands on the graphic and you'll have the correct answer. We are extremely pleased to have Steve Kastner in the studio with us today. Now, Dr. Kastner is a research scientist at NASA Ames Research Center in California. He has an airline transport pilot certificate with type ratings in the Boeing 737 and the Cessna Citation. He is also a Gold Seal certified flight instructor. Now, for the past 15 years, Steve has been involved in researching the way pilots learn to use advanced cockpit systems, such as GPS, moving maps, and autopilots, that sort of thing, and how these systems can affect pilot awareness, workload, and the types of errors that pilots make. Steve, we appreciate you being with us.
Oh, thanks. Good to be here.
Now, number one question. Many of today's pilots are transitioning from steam gauge instrumentation to this, the glass cockpit. How is flight training evolving as a result of that?
Well, I think there's two schools of thought here. One school believes we should be teaching pilots to use these systems that we're now seeing in the cockpit and to put their trust in them. Another school believes we should be teaching those systems in addition to all of the old navigational skills that pilots learned in yesteryear: time, distance, rate calculations, fuel calculations, and whatnot. So depending on your frame of mind here, some people believe that flight training is getting simpler, and some people believe it's getting more complex.
Okay, back to the classroom again with Josh and a new topic: types of altitude. See you in a bit.
Let's move on and talk about the various types of altitudes. We'll begin with true altitude. And true altitude is the vertical distance of the airplane above mean sea level, or MSL. Next, absolute altitude is the vertical distance of your airplane above ground level, or AGL. Next, pressure altitude is true altitude corrected for non-standard pressure. Standard atmospheric pressure is 29.92 inches of mercury. Pressure altitude corrects for instances when we are not flying at standard atmospheric pressure. In this example, the aircraft is flying in an area of non-standard pressure, with the indicated and true altitude both being 10,500 feet. If the pilot fails to adjust the altimeter setting to the current barometric pressure as he continues his flight, as shown here, into lower pressure, the indicated altitude would read 10,500 feet, while the true altitude is actually 9,500 feet, and this is a hazardous situation. Now let's take a look at density altitude. Density altitude is pressure altitude that has been corrected for non-standard temperature. Remember, standard temperature is 59 degrees Fahrenheit. Now, since you will often fly in non-standard conditions, you need to know and understand density altitude and how it's going to affect the performance of the airplanes you'll fly. This will be discussed in greater detail in Lesson 9. Indicated altitude, very simply, is the altitude read off the face of the altimeter. It's very easy to remember. Remember this: atmospheric pressure decreases about an inch for every 1,000 foot altitude increase. So if our standard atmospheric pressure is 29.92 at sea level and we climb 1,000 feet, the actual pressure is 28.92. Here's an example for pressure effects. Suppose we're flying with our altimeter set to 29.15 and we get a current altimeter setting from the tower of 29.85. That's an increase of 7/10 of an inch of mercury. So we have 7/10 times 1,000 feet, and this equals a change in altitude of about 700 feet. Check out this example. We're on a flight from a local pressure area of 29.92 inches to an area with a lower pressure of 28.92 inches. Now, our aircraft with the correct local altimeter setting of 29.92 is cruising at a true and indicated altitude of 4,000 feet MSL. If the aircraft proceeds to the area of lower pressure with the incorrect altimeter setting of 29.92, it will still indicate an altitude of 4,000 feet, when in actuality the true altitude is only 3,000 feet MSL. Hence the adage, from high to low, look out below. This example illustrates the temperature effects of non-temperature compensated altimeters. Let's say we're on a flight from an area of warmer than standard temperature to an area of colder than standard temperature. Now, our aircraft is at an indicated altitude of 10,000 feet, but because we're in areas of warmer than standard temperatures, our true altitude is actually 11,000 feet. Now, as the aircraft transitions to an area of colder than standard temperature, we can see that our indicated altitude is still 10,000 feet, but the true altitude is actually 9,000 feet. Now, the good news is that today most altimeters are temperature compensated, but the FAA wants you to understand this phenomenon.
All right, the different types of altitudes. Let's take a look at this question. Under what condition is pressure altitude and density altitude the same value? You've got 3 potential answers. Only one is correct. Have a look. Okay, under what condition is pressure altitude and density altitude the same value? The correct answer, C, at standard temperature. Once again, remember, when conditions are standard, pressure altitude and density altitude are the same. Steve, what's the basic idea behind the primary flight display?
Well, the primary flight display is easily one of the more interesting additions to the new cockpit. The first thing you notice about a PFD, or primary flight display, is that it's able to pack more information into a smaller space. What happened here is, as we started adding new systems to the cockpit, we couldn't have pilots craning their necks in all directions to gather the information they needed. So the PFD really integrates everything into one complete picture.
Back to Josh now in the classroom for a new topic, and that topic is gyroscopic systems. See you back here in a bit.
Let's take a look at gyroscopic instruments. These instruments employ gyroscopic force. Now, the first gyroscopic principle that we will discuss is called rigidity in space. Now, this graphic right here will illustrate rigidity in space. Now, rigidity in space says that a gyro rotating in space tends to stay fixed in its plane of rotation. When you attach this rotating gyro to a gimbal mechanism, it allows the gyro to stay fixed in its original position while the airplane actually rotates around it. Now, the second principle is called gyroscopic precession. Now, precession says that a force applied to a spinning gyroscope will produce a resultant force which is 90 degrees ahead of the plane of rotation and in the same direction of the initial force. Let's take a look at how that works in the next slide here. First of all, we can see that this gyroscope is rotating in this direction as shown. Now, if we apply a force to the gyroscope right here, where this red dot is shown, we can see that the resultant force will actually not cause it to tip towards us, but will actually cause it to tip right here where this red dot is shown, or really sideways and in the same direction as we applied that force. We can see right here that gyroscopic precession has caused that gyro to tip sideways. Here we have a typical vacuum pump system. This vacuum pump pulls air through and out the heading and attitude indicator. Here's how it works. The vacuum pumps air much like a home vacuum cleaner, but it's driven by the engine. The air is pulled through a filter, then exits the filter and enters the heading and attitude indicators. A gauge connected to these indicators monitors the amount of vacuum. The air then passes through the gyros in the heading and attitude indicators and powers an air-driven motor. This air-driven motor spins the gyro at a very high RPM. This high RPM produces the desired gyroscopic force, which provides the attitude and heading indications. As the air exits the gyro instruments, it passes to a regulator. Now, this regulator maintains the correct system vacuum pressure. The air then passes to the vacuum pump, which provides the pumping action, powering the system. Finally, the air exits the vacuum pump and is vented outside. There are two types of air systems. One relies on a vacuum, as just discussed, and the other uses a pressure system. Beach Bonanza aircraft usually use the pressure system, and most other airplanes use the vacuum system. Each one uses the same pump. In the pressure system, the pump is located at the air input side. A third type of gyro-driven instrument used in recent years doesn't use any of this. They use solid-state gyros that employ a vibrating solid-state device which outputs electrical signals in response to rotational and axial displacement. They are used in computer-derived glass panel displays. However, the FAA wants you to know vacuum systems, so we're going to study it in detail and talk more about gyroscope operations. Now let's discuss the gyroscopic instruments in detail. This is the business end of our attitude indicator, or our artificial horizon. Back in behind this is the gyroscope spinning on its gimbal mechanism and the vacuum pump that powers the gyroscope. Here's the face of the instrument shown right here. This is the miniature airplane right there, and it represents the wings of the airplane. This is the artificial horizon. You can see this line right here. Now you can adjust the airplane up and down on the horizon by turning this knob. Turning this knob up and down allows you to align the miniature airplane with the horizon in the instrument. Now these marks that you see right up here indicate bank angle from 0 degrees all the way to a full 90 degrees of bank. This next gyroscopic instrument is called the turn coordinator. Now in many instances these are electrically powered gyroscopes. However, some are still vacuum powered. The gyro in this instrument is mounted at an angle and thus responds to both yaw and roll. The turn coordinator provides a direct turn indication and an indirect indication of roll. While the miniature airplane responds with the airplane's banking action, it mimics roll. However, it actually directly indicates rate of turn. This means that in a 30-degree bank turn, the airplane will show a bank on the turn coordinator, but it may not actually be a 30-degree bank. Now below the instrument is a little fluid-filled tube and ball. You can see the ball right in the center, and this is called an inclometer or a skid and slip indicator. If you keep the ball centered using the rudder pedals, the rate of turn will be coordinated with the angle of bank. If the ball is deflected to the left, the airplane needs more left rudder, and conversely, if it is deflected to the right, it needs more right rudder. The last gyro instrument is the heading indicator, also called a directional gyro or a DG. Now it appears similar to a compass, and it shows the direction the aircraft is heading. In this case, we're flying 341 degrees. You can see that right here. However, it's important to understand the term heading is synonymous with pointing in this case. Just because the airplane is heading at 341 degrees does not necessarily mean that the ground track the airplane is flying is actually 341 degrees. Wind can have a great influence on the actual track. The heading indicator consists of a pictorial representation of an airplane moving along a compass rose. Assuming the heading indicator has been aligned with your magnetic compass, it will indicate the magnetic heading under the nose of the airplane. But unlike the magnetic compass, the heading indicator is not a true direction-seeking instrument. Since it does not have a magnetic compass reference, you must set it to agree with the magnetic compass. Some heading indicators provide for automatic remote magnetic setting and do not need to be manually set to the magnetic compass. The heading indicator also has a tendency to drift by a force called gyroscopic precession. Frictional forces within the gyro system cause the heading indicator to drift from its original alignment with magnetic north. To receive accurate indications during flight, you need to occasionally realign the heading indicator with the magnetic compass to counteract gyro precession. Some instruments precess quicker than others, so you need to check these every 10 to 15 minutes in straight and level unaccelerated flight. The heading indicator should precess no more than about 3 degrees every 15 minutes. The last instrument we'll cover is the magnetic compass. The magnetic compass is not a pressure-driven or gyro-powered instrument, and it requires no external power. The magnetic compass points towards magnetic north. When properly installed, it provides excellent primary directional information. All GA aircraft are equipped with a magnetic compass. While a simple and important instrument, it does, however, exhibit certain errors. Let's start with acceleration errors. First, assume you're in the northern hemisphere and the airplane is on an east to west heading. The compass will swing to the north while you accelerate and then return to the correct heading. Now, if you're decelerating on the same east to west heading, the compass swings to the south and then returns to the correct heading after deceleration. Remember the acronym ANDS, A-N-D-S, and it stands for accelerate to the north, decelerate to the south. It occurs only on easterly or westerly headings. The compass will indicate correctly when accelerating on northerly or southerly headings. Another compass error occurs during turns. The northerly turning error is based on the aircraft heading north. The compass will want to remain pointing north towards the North Pole when turning away from a northerly heading. The compass will lag or possibly even indicate a turn in the opposite direction during the first part of the turn. When you reach an east or west heading, it catches up and reads correctly. But as you continue with the turn to the south, the compass starts to race ahead of that turn. In fact, to roll out on a southerly heading, you have to turn past the heading on the compass. Just remember this acronym, OSIN, which stands for overshoot south, undershoot north. Now in the mid-latitudes, maybe as much as 30 degrees is reasonable for overshooting or undershooting when turning to the north or a south heading. Now deviation is the compass error caused by magnetic disturbances from electrical and metal components installed in the aircraft. The correction for this error is displayed on a compass correction card placed near the magnetic compass in the aircraft. Variation is the angular difference between the true or geographic poles and the magnetic poles at a given point. The compass magnet is aligned with the magnetic poles while aeronautical charts are orientated to the geographic poles. The variation must be taken into consideration when determining an aircraft's actual geographic location. It is indicated on charts by isogonic lines and is not affected by the airplane's heading.
Okay, welcome back for our last question of this lesson, and we're going to cover the compass here, magnetic compass, and some compass errors. The question is, when flying in the northern hemisphere, if an aircraft is accelerated or decelerated, the magnetic compass will normally indicate which of these three potential answers. Only one is correct. Please review. Okay. Question, when flying in the northern hemisphere, if an aircraft is accelerated or decelerated, the magnetic compass will normally indicate B, correctly, when on a north or south heading only. Now let's explain a little further here. While on an east or west heading, an increase in airspeed or acceleration will cause the compass to indicate a turn toward the north, and a deceleration will cause the compass to indicate a turn to the south. If on a north or south heading, no error will be apparent because of acceleration or deceleration. Remember, ANDS, A-N-D-S, accelerate north, decelerate south. Simple again, isn't it? Steve, with so little standardization in instrumentation today, what are your suggestions for how a pilot can go about learning these instruments?
Well, for one thing, I have to say that in the future, we're going to need to do a better job of designing these computer interfaces. There are ways to design a computer interface that sort of makes the next step that you need to do, a little more apparent than what we're doing now. So there's certainly some room for improvement. For the time being, for the pilot, all I can say is you're just going to have to practice on a regular basis to get these keystrokes and button pushing procedures in your head and make them stick there.
Okay, when you're ready, we'd like you to move on to lesson number 4.